Very good morning and selamat pagi to all of you. Nice to see you here again today. Today we will go through the components for automations and process control. Just a quick recap on what we have gone through last week. Okay, so you have seen these presentations previously where we highlight there are several basic components in an automation system that includes motors, actuators, sensors, and so on and so forth. So here there are some important, or maybe the parts that do the hard work, okay, which we intend to replace a human, okay, which we use motors, actuators, sensors, and handling. And today's when we talk about hardware, okay, we are referring to these several components, okay, that includes the motor, sensors, and the handling device. So you can see that we just exclude this indicator because it's just an indicator. It can be in a monitor form, I mean screens, or maybe the light, right? So okay, so we can break the hardware into three major parts, okay, the actuators, okay, the sensors, and the handling. But in this presentations I will have four categories basically regarding the actuators. Then one part is about the relay, another part would be the sensors, and the last part the handling devices. Okay, industrial automations circuits. Alright, so when we talk about automations during the planning sessions, we would want to come to a, maybe we always call a drawing board and so on, right? So nowadays we will just draw everything on the computer, okay, for the young generations. But still in the older generations we used to draw, we sketch first, okay, before we translate it into the digital form, okay. That would give us a freedom to sketch, cut here and there before we actually put into the nicer or neat pictures, right? So in the electrical circuits, okay, when we deal with the automations, we would want to tell what are the components or how they are operates in general, okay. So here in the electrical circuits, generally we can divide them into three main circuits or drawings, okay. The first one, the power circuit, then the second one, the automation circuit, and the third one, the wiring diagrams, okay. So here the power circuits basically tells us how we can power the device, okay, how the power comes in, okay, through the main power, okay. In the factory it can be a high voltage, okay. In a house or normal SME, then it can be just a 240 watts supply, okay, and how it is being connected to your power device, right? Then come to the automations part, okay. Then we would want this automation circuits, okay, that may include maybe a control and auxiliaries, secondaries, or others type of circuit that illustrates the operation logics, okay, how the flows come in, okay, where is the stop buttons, how it operates, okay, through which devices. All right, so you can see that simple automation circuits may have a stop button, the start button, then where is your relay contact, okay, your relays, and so on. So this would be your power, okay. So you have the power supply, okay, and the neutral line, right? So assuming this is only 230 watts, okay, so this is a simple one, right? So also in the automation circuit, when it become more complex, then we will have more lines connecting them together. So in a general practice, you will see that we always draw two lines from top and bottom to to denote or to give us the ease to connect to the power supply, right? Just like prototype board itself, okay, you may have a power and power supply at the top and bottom, so you will connect everything in between, okay. That is the general idea when we do this automation circuits, okay. So when we will go to the wiring diagram, okay. So wiring diagram actually a combinations of all this power circuit as well as this automation circuit. So you can see that the power circuits we generally would want to draw it in a single line diagram, okay. So this is a single line diagram, okay. Even though it is a three phase, okay, we just draw a one line, a single line, right, with three there, so it represents single line, and it is simplify how we can power the motor, right. So we can power the motor, but then in the more detailed part, okay, of the automations on this part, okay, after the fuse, then we would want to have a simple control circuits, okay, that include the stop buttons, start buttons, the relays, and so on, okay, before it's connected back to the neutral line, okay. So you can see that sometimes, okay, or most of the times, we can separate these two circuit, okay, from a high power part, the motor, the device part, okay, and the automation part where we only want to control, okay. It can be in the form of a simple board, okay, PLC, and so on, okay. So these are the control circuit part, okay, and in between them now we would come across some wiring to connect them together, okay, from the bigger hardware, okay, and your automation circuit, the circuit board type of hardware. Alright, so when we combine them together, then we will have this wiring diagram, how we can connect them together. So we have this representations of a simple automation circuit where it should be looks like, okay, how it should looks like, and where the buttons should connect to the wiring in the power circuit, right. So this is the idea of how all these automations can be represented in a drawing form, okay. As the industry automations have evolved, you can see that the task of controlling process have also evolved throughout the years, from very simple manual operations, just start, stop, okay, then it comes to the analog low level of automations, okay. It can be as simple as the toilet flush mechanisms, okay. You just flush and then it will automatically fill up until a certain level and stop, right. That is a very low level type of mechanical type of automations, okay. It automates to the filling of a tank in your flush systems, right. Then towards now, as semiconductor progress, okay, internet progress, then we slowly move into the computer. We digitize all these signals, informations in the form of input as well as the output, okay. Then from there onwards, we move on to the IR 4.0, where we want to capture all this data, process them in a separate way or in a more intelligent or smart way, okay, to help us to give fast feedback, okay. As human cannot monitor every single signal, okay, this kind of intelligence will be able to help us to monitor or detect all this sign, maybe a sign to failure, a sign to whatever it is, okay, depends on the intelligence itself, right. So in the digital device, we can have a personal computer, okay, with the I in front, okay, industrial personal computers, then PLCs, PACs, and so all these are just I would say terminologies, okay, developed throughout the years by the industry, okay, to be able to apply or control, okay, since 1970s. Alright, so automations has start to evolve. Okay, slowly we add in years by years. Okay, the sensors, the capability of sensors, and the computational unit itself. Right, then come to a point where we would have this SCADA, right, a supervisionary control and data acquisitions. Okay, so all this data will be captured, okay, and recorded somehow, or maybe transmit to interface screens, okay, in a remote area. Okay, it can be a view, maybe you have operations in Kelantan, another operations in Johor, and I'm going to monitor it at maybe Penang, right? So you can have this SCADA system through internet, or maybe in a local plant itself. You may have plant 1, plant 2, plant 3 at a single area. Okay, so you want to monitor them at a single place. Okay, so you have this supervised SCADA control system, right, and so on, right? So you would see when you start to work, then basically you may see different naming, right, from different maybe manufacturers and so on. Okay, but the concept that how they evolve or operates are more or less the same, right? Only the naming may be slightly different. Okay, they to highlight their own advantages and so on. Okay, that is the patented part, right? Then in the PLC and PC, as we can see, as the progress of the hardware or the computer systems change, okay, then people will tend to move to the PC, especially for younger generation, which being exposed to the computer or PC since they are born, right? So you can see that by the time you were born, then the markets or the offices, okay, already start to use PC in almost 80 or 90% of the offices. Okay, so you can see the adaptations of PCs are very high in the later in this latest generation, but it's 10 years later, okay, in the time of maybe those born in maybe 2010 and onwards, so they are start to expose to all these smartphones, so the exposure to the smartphone instead of PC is higher, right? So you can see the change in how people interact with the digital content. Okay, and that also shift slightly shift towards to the industry to meet their characteristics of how they interface with machines, right? So for sure, PCs offers very good computational power and flexibility in interactions. Okay, whereas PLCs are mainly designed for the tasks of the industry. All right, so they are very durable. Okay, that everything's are optimized. Okay, and it can last there for many years. Okay, it can full run 24/7, okay, for many years, okay, without fault, okay, unless something happens, right? So very less chances that it will get fault. Okay, so in a computer integrated manufacturing model itself, we can see that there are different layers. Okay, so I guess you may have seen this or learned this before. So okay, so you can see the field itself. In the field level is where most of the hardwares are located. Okay, you have the robots, okay, the motors, the pumps, and other things. Okay, so these are time critical field network. Okay, that you cannot break down. Okay, so if it break down, it will send a signal that error. It doesn't tells how it should be processed in the next station itself. So therefore, these field levels are critical, are time critical. So they are connected to all these controls. All right. Then next would be the control level, where you have computer. You start to have more wider computers to see maybe one plant or maybe one stations, okay, or maybe several stations to see the overall. Then this is would be a time and control critical network. And in the later stage, okay, in the managerial level, okay, then you will want to see mainly information, how they are being collected, okay, what is the temperature of all this information. So you can see this is a SCADA screens for visualizations, okay. Visualization means you can see this actual screen in the factory. I believe you have, some of you may have seen this, okay, in the factory, where you can see the temperatures on the screens, okay, in a so-called real time, right? So these are the level that you can see, right? So now we would come to the hardware part, okay. First we will introduce these actuators. Actuators basically is a device that produce the motions, okay, to replace our hand and legs, okay. It produces the required force and motions in order to actuate, to move object in the desired manner, okay. So all these actuators should be able to be controlled, okay, it's controllable. And there are several types of actuators based on the operating principles. We can divide them into a thermal, electrical, hydraulic, pneumatic, and ambience, okay. Here is the electric motor, right? So electric motor again is a kind of actuator, okay. It can have several categories, okay. Stepper motor, servo motor, linear motor, solenoid type of motor, and so on, right? So, and also they are being powered by AC, DC, okay, depends on the applications or the control of your circuit or process itself, okay, depending on those things, okay. And for an industrial engineers, okay, most of the time the motors are categorized separately with other actuators, okay. The electric motors are defined mainly for the high power productions, okay, mainly for rotary type or linear type, okay, where we have a very high power input, okay. It can be from a three-phase and so on, okay. That is how they use the term to separate them, okay. But in general they serve the same purpose, to actuate an object, okay, to produce a desired motions, okay. Also motors are important. Sometimes you should able to reverse them, okay. To reverse the motor you just have to reverse the polarities, okay, of the winding itself, okay. So you can see the motors are used in the pump, okay, to power the motions of the centrifugals mechanisms inside, okay. Then also we have a motor and also another electric motor in a fully electric car, okay. So I'm not sure if you have gone through this in details or not, okay. But here I just want to highlight certain characteristics of the motor, okay, that's all, okay. So in the motor, when we do a selections, the characteristic curve would be the important informations where you will start to use, okay. That is the main curve that you would want to refer to, okay, when you do the selections of a motor, right? So in the motor itself, in the AC motor itself, you may see several lines in the same curve, okay. This red line represent the top curve, okay, and this solid black line represent the current curve, okay. So these two curves are useful for you when you want to see what is the suitable, I would say, what is the suitable operation speed, okay, to power, okay, and what is the current, okay, that you need to supply to your motor itself, okay. And this dotted line represent the load, okay. the load curve. Right. So at rest, the motors appears in a short circuit type. Okay, so when at rest, when we have 0% from the full speed of your motor, then we need it is so-called lock at that positions. Okay, so it will produce a lock rotor torque. Okay, using or with the supply of lock rotor current. Okay, so this is the current that you need to supply to lock the motions of the motor, right? So now in our discussions here, we would say that the voltage are now keep constant. Okay, so assuming the voltage is constant, only the current is changing. Okay, so here you will see that the motor will change characteristics according to the speed. Okay, as we adjust the speed of the motor, then the torque and the current being drawn, okay, would change accordingly. Okay. Here we see that when the voltage is constant, so the starting motor, the starting current of a motor will drop slowly at the beginning. Okay, will drop slowly at the beginning, and will start to drop significantly. Okay, roughly about 80% usually. Okay, it will drop drastically here. Okay, yeah, we will drop drastically there. Okay, until the full speed. Okay, so it will draw all the currents to move your motors. Okay, to rotate the motor. So generally, a good motors will have a currents range from maybe 550 to 750 of the full load current. Okay, so we would don't want to operate our motor always at very high full load current. Okay, so that's why when we actually run it at the full load current, so it gives us a very good performance. Okay, and lesser heating. Okay, then also at the top curve itself, then we'll see two main point here. Okay, one is the minimum point, we call it as a pull up torque, and the maximum torque point where it is a pull out torque. Okay, so these are the 2 points where we will try to these 2 informations are useful for us. Okay, so we would want to operate most of the time at the maximum torque, right, if possible. Okay, but then it depends on your application, what is the speed. So you should able to find a motor or select a motor that operates as your desired speed and produce your desired torque. Okay, so you cannot very rare that you may operate a motor all the time 100%, okay, of your rated speed. So that because the desired speed of your operations may varies. Okay, so this is where you may want to varies and make sure that when the speed that you have selected, it should also it should provide the required torque to actuate your operations. Okay, so this is where the regions where you may want to check. Okay, so here, if in the case of the load curve is added, so when if we have a load curve is added, then we will know what is the operating speed and torque, okay, that are suitable or being used, okay, during that load. Okay, so this is the load curve, and you will see how it should change accordingly, right? For stepper motors, we also have characteristic curve, okay, as shown. Okay, but here it's more straightforward. Okay, from a very high point straight to the bottom. Okay, it's just going down, right? So here we have again 2 torque. Okay, so this is mainly on the torque itself. Okay, as a stepper motor, we don't calculate or we don't describe the speed in terms of percent, okay, because it is on the response of the motor itself, on the programming of the motor itself, on how it synchronize our movement or rotations of the motor, right? So here generally we have a maximum speed, okay, being defined. We are not calling that as a full load, okay, because at this point the load is now 0. You can see that the torque itself actually dropped drastically down, right? It's not going up and so on, right? So you can see the maximum running speed is here, okay, and there is another maximum no load starting speed, okay. So this is when you don't start, okay, it still produce a certain load curve, right? So this is a no load curve, right? Okay. So in order for us to hold an object, okay, then the motor itself will produce this holding torque, okay, when it doesn't give us any motions, 0 rotations, okay. So this point represent the holding torque, right? And we have this called slew range, okay, and this regions is where you usually want your motors to operate, okay. Stepper motor actually could not start or do not operate well, okay, to start at this range, okay. You should start at this range first, okay, before you shift it to your desired range. And when you want to stop, then you slow it down, okay. You slow it down first before you stop it, okay. So this is how you avoid the motors getting jammed, right, in between that, okay, because this is how it operates, right. So when designing or selecting the stepper motor, this consideration should be taken into account, right? Okay. Next is the pneumatic actuator. For pneumatic actuators, it's more straightforward, okay. It's a simple piston cylinder assembly that connect a supply of a compressed air. For sure, since the air is highly compressible, this kind of actuators are mainly used not for precision type of control, okay, because it's highly compressible, so it can easily be affected by the load, okay, the movement of it. Then the applications for it will be limited to a simple and discrete control operation. Discrete means on and off, okay. So you may want to use this kind of pneumatic actuator just to push pull, okay. So in a machines, okay, you may able to use this to maybe open the door, close, okay. So you will see these operations are repeatedly being used, okay, pushing objects in the conveyors and other things, right. But then this pneumatic actuator have an advantages of being very clean, so-called very clean, because it's only using air, okay. So you don't have that problem of contaminate your system with oil, no leakage, okay. If you leak air, okay, not the oil and so on, okay. So the operations is very similar to hydraulics, okay. But hydraulic will apply a non-compressible fluid, and because of that it can also use for very high force and more accurate control, right. And then now is MEM systems is a process or technology based on the technique of micro fabrications, okay. We intend to produce something at the micro level, okay. So this micro level will have this electromechanical system embedded inside, okay, to create a device for us to maybe to sense, to control, or to actuate, right? So since this is a actuator, then most of the time we would incorporate all these three elements or two functions inside this so-called system at the micro level, right? Here is an examples of micro valve. Okay, so you can see that the path of the valve will go through it. Okay, so in order to open the valve, okay, so you will have a actuator here by maybe magnetic, okay, or other principle, electrostatic principles, okay, to on and off this to open and close this particular valve, okay, a very small valve itself, okay. And they can be categorized into four basic groups: electrostatic, piezoelectric, magnetic, and thermal, okay, depending on how the systems or the principle of the system to operate the actuators itself, okay. So here is also a micro actuator. I will say this is micro actuator. Here is another example of a micro actuators, okay, where you can see that initially it is straight, okay, then using electrostatic, then this part will now stick down, okay, then after that slowly move, okay, because of this movement this part will start to shift forward, okay, and then when it release again, then you actually have moved forward a little bit, okay, at the micro level, okay. So also in recent years, because of the development of 3D printing technology, they would also try to investigate how we can fabricate MDM device, okay, or switch in this case, okay, how we can print this switch, okay, to electrically control it, okay, just power at the both end and you start to behave with this actuation on and off, okay, electrical sort of switch. Here is solenoid linear actuators, okay. So in this solenoid linear actuators, the functions is to, again, using solenoid, it means we are using electromagnetic principles, okay, and we use that principles to actually drive our actuator, right? So by converting that, we will be able to push, okay, magnetize certain part and push it forward, and or maybe push it pull it backward, okay. So here is a type of motions that we can electrically control using electromagnet, okay. Next is a relay, okay. So as I have mentioned previously, in industrial automations, power relay plays a very important role, okay, and it is because in the automations, it's play more on to turn on and turn off a certain operations, okay. You want to push bottles away or pull a bottle away from your conveyor belt, so you will always want to turn it on, turn it off, turn it on, turn it off, and so on, okay. So there is a repetitions of work, okay, in executing or doing the repetitions of the work itself, okay. So therefore this so-called switch is very important, okay, in order for us to electrically control them, okay, through switching, okay. So synonyms, instead of using relays, sometimes you also see magnetic contactor, they are remote operated switch, and so on, okay. So they are just referring to the principle of relay, okay. Here the principle are very straightforward, okay. They use electromechanical device to open and close the switch, okay. So in the relay itself, you will see that there are two parts, okay, just like your industrial automations setup, okay. You will have a power part and there is another part as the control part. Okay, so at the control part is how you can use a small voltages, okay, or current to actually operate this switch. Okay, whereas this switch will control the bigger power part, okay, the power circuit. Okay, you have a motor at a high power, okay, connected to this switch. Okay, and how you going to operate this is through this simple electromagnetic principles. Okay, magnetize, demagnetize the operations, and this particular sections, okay, auxiliary plus this switch part, okay, is the whole constructions of the relay. Okay, general purpose of the relays would be as auxiliary components, okay, for the implementations of the industrial automation circuit, meaning to say you may use one relay to control multiple relay as well. Okay, so that would be a way of using it. Okay, and then switches to supply a very small electrical load, okay, to maybe a valve, or this one is more direct, okay, connecting to your devices. Okay, here are the figures or the constructions of a power relay and a general purpose relay. Okay, so the power relays, as you can see, these are commonly available in most of the process plants, okay, where they are stacked or arranged together. Okay, so here this part is the relay, and inside you have the moving part, right, and the electromagnetic part. Okay, so this is the auxiliary part, okay, that to control the contact, okay, of this switching. Okay, then for the general purpose part, also very similar, okay, in the smaller scale. Okay, and you can see all these small relays. That's why in the operation of the relay you will always hear tak 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 tak, the sound of the switching. Okay, if it is operating at a very high speed, then you would keep hearing this switching, right? Other type of relay, yes, there are a lot of different type of relay. Even today's we cannot cover everything, all right, just a general idea. These kind of devices are, or relay has exist, okay, to help different needs of the industry. Okay, so those relay, as you can see previously, they operate when the power is on and off, right? But then sometimes you may want it to keep the previous state, okay, meaning the last state of where is the position, whether it's on and off. Okay, we don't want it to, when you turn it on, then or power it off, then the contact is at the preset conditions. Okay, so we want it to have a so-called some kind of memory. So we have this latching relay, and or we some other text. Okay, in Wikipedia, this picture they say is a memory relay. So they have these functions that store the last, or to maintain the contact positions of the last point, okay, before the power is being removed. Okay, so you may have, instead of on and off, I may want to say state 1, state 2, right? So there is this memories. Before you turn it off, it may at state 2. Okay, then after you do certain things, then you will go back to state 1. We don't want to, every time we turn it off, then when we turn it on, it is go back to the state 0, and so on, right? So inside there would be mechanical mechanical constructions, okay, that helps us to store that state itself. it can be mechanically, you can see it can be mechanically or magnetically locked at that state. Okay, you may have two magnet, permanent magnet, so when you stick to one side, when you remove it, then you will stay there, right, before, unless you give another force to switch it. Okay, so this is the way of you keep the memory of the previous state, okay, even though you have removed the power supply. Okay, then come to a smaller part, okay, electronic part. You also have the solid state relay. Today you have a solid state drive and so on. So this is where the semiconductors comes in, okay, instead of a very big, okay, now it slowly evolved to a miniatures part. Okay, so all these electronic device in the solid state relay do not have I would say mechanical constructions, okay, and therefore it is more quiet in a sense, and also, yeah, you would say it may last longer somehow, right? Okay, but not sure, we will see how it will operate, but they are very sensitive to temperature, right? So yeah, this is how you should able to see it, okay, because they are semiconductors. Next, we will have this electric contact classifications, right? So in dealing with the relay, there is this switching, okay, and this switching basically is the logic that you have learned previously, okay, from 1 and 0, okay, so this kind of digitized state of the contact, right? So the electrical contact of a relays may have one or two throw, they call it, okay, so okay, remember the contact itself may have one or two throw, okay, so this number of throws actually indicate how many different output connections that the electrical contact has, okay. It may have one, or in this two throw you have one and two options, okay. You may switch between these 2 points or two points, okay, or two nodes in this case, alright. So this is what we call contact, right? So we call it throw, right? For a double throw itself, generally they will also call it as a changeover contact, okay, changeover from one state to the other, right? So this is a common double throw sign, okay, or symbols. Okay. And then we have this common terminal, the input, alright, the common terminal. So now the relays or the hand switch side, okay, may also contact or consist of one or more individual contact, okay, referring to as pole, okay. So we have one pole, or in this case 2 pole, or more than 2 pole, right? So therefore a relay, you would see either one throw or two throw, okay, most of the time one throw or two throw, but for the pole you may have one pole, 2 pole, 3 pole, and multiple pole, okay. So you have a sign of single pole, double throw, okay, double pole, double throw, okay. So these are the common industrial naming, okay, of these relays, okay. You can easily search for the type of relay based on this naming, okay, in the supplier chain itself, right? So this is how it would look like, okay. The relay itself, as I say, relay is one part, okay, and the contact is another part, okay. The contact of how it would operate or power your motor or actuators, okay. Whereas the relay side is how you want to control it, right? This one is how you want to power the other side, okay. So, and they are related, okay. So when we use a relay, okay, that they say is normally closed NC. Okay, so again, these two terms will be commonly used in a relay. Okay, normally closed or normally open. Okay, NC and NO. Right, so don't read this as no. Right, so this is NO. Right, so what it means is that normally closed means when the power is not there, then they will close the circuit. Okay, this is what they call normally, right? Then if your relay doesn't give any power for NO type of relay, then at that stage it's always open. Okay, this is the state of it when they are not energized. Okay, your relay is not energized, and they will do the vice versa operations. Okay, when they are energized. Okay, so same thing for the double throw and multiple poles type. Alright, but then here you will see that they have two parts. Okay, you can now pick, okay, whether you want it to be normally closed or normally open. Okay, then once you set it, then whenever you energize your relay, then you will switch positions. Right, and also because of that, you can always set multiple settings for your relay side, and in one input control, it will control multiple switching on the other side. Next would be our sensors. Okay, sensors play a role to sense, to give us a feedback. Okay, whether it's enough or not enough. Okay, when we do the things. Okay, like when I grabbing a glass of water, so it will sense or tell us it's reaching or not. Okay, so these sensors are very important to tells us the state of the control of our process. Other synonyms of these sensors can be transducer, emitter, and so on. Okay, so and also sometimes they also act as a switch. Therefore, the terminology are somehow blur in between. Alright, so nevertheless, as long as it functions to detect the state of your control, then we should understand that that is a sensor for us, right? So there is a very different confusing terminology, but as long as it gives us the idea, okay, what is the current state, okay, of your control process, we would say that have the sensors type of functions, right? So here is thermal overload relay. Okay, and as you can see, this relay, the name still relay, but then it has the functions of protecting the operations, okay, or the motor from being overheated. Okay, we call it thermal overload relay. So the function is to protect the motor from overcurrent, right? And because of the overcurrent, it will cause the damages to our motor, right? So you can see that in this relay, it has the sensing part where it senses whether it's too hot or not too hot. But then in the way of maybe not in the way of measuring what is the temperature, right? But then in the way of at this certain cut-off temperature, okay, then you will start to kick off, right, the operation. So you can see that there is a bimaterial concept. Okay, so this bimaterial concept is very common in the industrial automations process. Okay, you will see this in many relays and so on, and it is flawless, I would say, unless some mechanisms hold it off. Okay, otherwise it's flawless because you don't need to program it. It is functioning as such, right, due to the behavior of the material. So when you heat it up, okay, at a certain stage of the current, when it's too hot, okay, then start to bend, okay, because of the different thermal expansions characteristic of material, okay. So one side will expand longer than the other side, and you will start to push or pull this latch or lever, okay, in order for us to maybe to close or open a certain operations, okay. So this is how it will operate. So in this sense, what we need to set is we have to set our nominal current, okay. So if it's more than the nominal current, then it will start to stop our operations. All right, so this is how it will operates. Then for the limit switch, this is a very conventional mechanical type of switch, okay. It's just push, okay, then you will see that it will operate, okay, with a return spring maybe here or here, depends on where yeah, it will operate like this, and depends on whether you want it to be normally closed or normally open. So if you connect to normally open, so in the state where you don't press this or actuate this one, or then the circuit will be open, okay. If you connect your circuit to this normally closed one, okay, so before you press, it's already connected. Until you press, then only you will disconnect you from your power, okay, to your circuit. And to operate this plunger, okay, you may have this actuator head, okay, and this actuator head can be in various form, okay, depending on your needs of your operations, okay. So these are the fork type, okay, where you can switch sides, okay, on to detect the motion maybe from this and from this, okay. Where other type may have this adjustable roller arm type, okay, where you can detect motion in this way, okay. When the motion comes in this way, okay, it will push this to go in, right. That's why you need this roller to be there, right. So when the motion's coming in here, right, passing through this you push it down, right. So this arm is adjustable. So in that sense, the limit switch have a kind of touching sensor, okay. It may touch your product, whether your product have come to your hand or of your machines, then it will touch and tells this is the current state it has start to touch, okay. So you should do something, right. So usually it will be put at the end of constructions or your mechanism itself, right, to detect maybe it have reached the end, okay, of your operations, right. Then now we have this non-contact detection type, right. We call it proximity sensor. So this proximity sensor can operate based on different operating principle, whether it is inductive type, okay, to change the inductions of your circuit, internal circuit, okay, when some object come close to it, right, or maybe the capacitive or a magnetic, okay. So it will sense in that way, okay, a proximity switch or sensor, right. So again, you can see that they call it as a switch because it may switch on off, okay, in the construction itself, alright. Once it sense it, then you will do the switching, right. That's why in the industry they many times they want to do or to know the state of it, alright. So that's why the word switch are very common, right, even though the function is to sense, okay. There are several advantages over the limit switch, such that no mechanical movement, okay, long electrical life, more durables in the sense of motions, okay, because this one can still move a little bit, okay, and it will still work, right. And for the toxic environment, okay, where you don't want your switch to keep contacting, or maybe there is a chemical when you contact for a long time, you will have a I would say wear or tear and so on, right? Yeah. And also this is very effective for high speed switching or high speed detections, okay, whereas for the limit switch you may need to really touch it until the end, right? So you may have a limit of switching frequency, okay, when we deal with the limit switch, whereas this proximity switch, they have this very high speed of excitations, okay. Here are several examples of applications of the proximity switch, okay, depending on how you want to place it, okay. You may want to place it where the motions of the object is perpendicular to the axis of your sensors, or you may also want it to be placed the object movement growing directions, okay, is along the axis of your proximity switch, okay. So here is several examples. For example, this one, you may have this slot type of proximity to actually detect whether the production is continuous or not, right? So this may be useful for maybe paper or fabric, okay, to detect whether the paper have finished or not, right? So they will continually sense whether there is or not something's there, right? There are several parameters or characteristics of proximity switch that you may want to consider when you deal with the selections, okay. That includes the detections distance, okay, how far you can detect, and then the placement distance, okay, how far you want to place your object, okay. So detection distance, the maximum distance that it can sense, right? So more than that it will not sense, okay. So here this detection distance will play a more important role when the object is moving in the parallel to the sensor's axis, okay. So when it close enough, then it will start to sense, right? So this is how it is operating. So by controlling or selecting the maximum detection range, then it will helps you to detect or not detect the object, okay? Whereas for the placement distance, then you will have a constant distance that you want to set, right? So let's say you set this as your constant distance, right? So whenever your object passing through it, right, so it will start to count, right? There are something passing through, and your switch will now switch on your operations, okay, or your state itself, right? So make sure that the placement distance always within the range of your detection distance, okay. We cannot have this away from your detections distance, okay. Then also the response time is very important parameters when we want to deal with a process, okay. If it is very critical, then the response time become more important. Is referred to the time elapsed between the object detect and the output, okay. Sometimes the object move very fast, or you don't want to detect your hand passing through, okay. So if your hand passing through very fast, okay, it may not detect, okay. That is where the response time of your proximity sensor is important, okay, depending on your application. If you are sensing something very fast, then your response times should be very short, okay, so that you can detect this kind of high speed movement, okay. But then if it is not moving at that particular high speed, then you may want to increase I would say respond slower, okay, so that for all this very high speed, maybe something dropping, okay, very fast, okay, that is not something you want, right? Then it will not detect, okay. It depends on your applications, right? So that refer to the response time, okay. Then also the operating frequency, how fast it can switch between on and off, right? They are measuring in the per second manner, okay? And the last parameters would be the residual current, okay? So this residual current would be the current that flow through the switch itself, okay? Because you need power to turn on to operate this switch, okay? So there is a current actually flowing through it, okay? Even though it may not being activated, alright? So there is a residual current within it, right? And this is very important, especially when you try to connect it as an input, okay, to your PLC, right? So here is the way of connections, okay? So again, the proximity sensors, some may have 2 wire and some may have 3 wire, right? So 2 wire and 3 wire proximity switch, okay? For a 2 wire type proximity switch, the residual current will now flow, right? So when you switch it on, okay, the current will flow in, okay, and go out, okay? So the current will always flow. We call that as a residual current going through the load, okay? And this is your load, right? So no matter what it is, because of you want to operate this the sensors, there is current that must flow through it, right, to operate. So your load will always have a current going through it, okay? So if you use that load, this load, let's say you are using it in a PLC, then your PLC will always detect a signal, okay, coming in, right? So that is why the residual current may become important, okay, when you deal with using it for a programmable part of a circuit, right? Yeah. So in this 2 wire connection type, then you may want to have this rotary switch, okay, to switch it, okay, during rest time and so on, okay? And when it's operate, then only it will switch on, right, to deal with these things, okay? Whereas for a 3 wire connections, then it will somehow bypass your load. The current will flow through it, okay, to power the sensors, okay, until when it switch on and so on, then it will tells you a different signal to your load itself, okay? So this is where it may be useful for you to use it as an input, digital input to your PLC, right? Then also the proximity switch will react differently when the size of your object varies, okay? If it is big enough to cover the area of your sensor's effective detection rate, then it's fine, okay? But then when the size is getting smaller, okay? When it is smaller than what it the detectable area, then this maximum distance of sensing actually reduced than what they have described in their catalog, okay? That is the maximum distance, sensing distance, right? Okay, but if you are using it to sense a smaller part, okay, the maximum detectable distance will now decrease actually, okay? So you have to adjust accordingly when you want to detect a smaller object, okay? Similar because of that, okay, if you have a uneven subject or object with a curvature, then the detectable area may be very small, okay? So in that sense, you have to take care of this so-called detectable distance, okay? Besides that, some proximity switch also sensitive to maybe materials, okay? Because they are testing it most of the time with the standard material, but then if you're using different type of material, using for different. Remember, you have different type of proximity switch depending on inductions, capacitance, and magnetic. So if the material change, okay, or if you affect the magnetic field or the induction fields of the operation, then that materials will have this kind of effect to your proximity switch. Okay, so you have to take care of all these things, okay, when you use this proximity switch. Okay, whereas if you use a limit switch, you don't have to deal with all this problem, right? Then another very common switches nowadays is the photoelectric switch. Okay, they are using a light, okay, a photoelectric. So these lights can be UV, infrared, or whatever it is. Okay, it's a photoelectric switch that you have. Okay, you have this switch also in your normal mouse, right? So you have a mouse here, right? So this mouse actually have this kind of switching. Okay, so this switching is, we call it diffuse reflective type. Okay, it detect the object directly and depends on the object to reflect it back, right? So this is a diffuse type. Okay, whereas if you need a reflector, okay, to reflect back all the time, okay, then we would call that as a retroreflective. Okay, meaning to say your detection object will be in the middle. Okay, you have a sensing distance. Okay, so when this move in between them, then you will start to block it, and because of the blocking, now they will detect that the signal is not coming back or as they expected. Right, so this is how it works. Okay, same thing for this. Okay, but then in this case you have the emitter and the receiver is being separated by two plates. Okay, why they have this kind of constructions? Okay, it depends on the advantages of the range of how far you want to detect. Okay, for sure this one you may not able to detect very far, right, because it depends on the reflective of the object. All right, so if it doesn't reflect much, then your design of your circuit may be difficult of waiting, okay, whether there's signal or not, okay, whether this signal is really that kind of signal or not, right? So that kind of unpredictable environment should be removed, okay, whenever you use this kind of diffuse reflective. Okay, whereas when you have a reflector, then you now predefine your sensing distance. Okay, this sensing distance now will be very far away. All right, so you can sense it from one point to the other. Right, that's why it is very useful in the manufacturing production line, where you have a conveyor belt, maybe a very long conveyor belt, a very wide conveyor belt, where the normal proximity sensor may not able to sense it, right? So this is this proximity this photoelectric switch will now come handy in that sense, okay, to sense a long range object. Okay, so again, this is how it operates, just like a relay. Okay, your relay, when a relay will come like when there's power on, there is power off, whereas for proximity photoelectric sense will be if there is a light coming in or there is no light coming in, right? So light on, dark on, right? Depending on the type of photoelectric switch. Okay, therefore light on when no object is going through. When the object is blocking it, then you will know that something is there, right? And this is how it operates, right? Next would be the lever switch. Okay, for the lever switch, here we will use it to detect the level of the liquid. Okay, so most of the time you want to know how high is our fluid, okay, being stored. Okay, it can come in a mechanical form or electronic form, right? So most of the time nowadays we will prefer electronic form, okay, so that you can easily acquire the signal remotely. Okay, so here is a electronic level switch with a being used in a conductive liquid. Okay, so the liquid itself must be able to conduct electric. Okay, that is the main part. Okay, so you will put it at a different level, and because of that it will start to conduct electric, right? And we detect which level it is being activate. Okay, depending on the level, then you will know what is happening. Okay, and by programming them together, okay, you will also know that whether the level is going up or going down, right? Then you have also the capacitive type of level switch. Okay, this one will depends on the capacitance of your material, of your fluid, or maybe a solid. Okay, that's why here this bulk solid can be a sand or powder form of things. Okay, so in this capacitance level, it will be useful because it now doesn't depends on the liquid to conduct. Okay, therefore you can use it for non-conducting liquid as well, right? Similar to this ultrasonic level, it can be used for different type of liquid. Okay, whether it's conducting or not. Okay, sludge or solid material. Okay, because this ultrasonic, it depends on the sound signal, right? So this sound signal will now detect how far it is. Okay, it can be in the form of non-contact, in this sense non-contact, or in the form of contact, where you have two parts. Okay, your water level will now filling it. Okay, so it will disturb the flow of your info, the ultrasound itself, right, to detect the level of it. Also, you have the float type level, float lever switch itself. Okay, this one just like the mechanical float itself. Okay, but because of this float, you have this pin itself being connected or disconnected. Okay, so when you start getting closer, it will push it to touch, right, the red switch in there. The red switch is there. And also the other types of optical level sensors. Okay, by using the optical photodiodes. Other types of switch now would be the flow switch. This one is to detect if the liquid actually flowing or not, right? Or in other words, also you may want to detect whether how fast it's being flowing. So if you want to know whether it's flowing or not, there are several techniques. Okay, so this constructions with the pedal type. Okay, you pedal it, right? Meaning to say you have several pedals, maybe one or several pedals in between. Okay, so you will keep rotating. Okay, so once it keep rotates, okay, or flip, I would say, flip instead of rotating, so you will start to tell whether the flow is moving or not. Okay, so as the flow increase, then this pedal will now switch to a certain angle such that this will move further, right? So this is how it operates. Then another type will be the thermal dispersion flow sensor type. Okay, where it will give us some heat, okay, and sense it at the later part, right? So once you put in some heating here, okay, you want to measure it, okay, whether the heat, what is the heat coming back or the temperature coming back, right? I would say it's a signal, right? So remember, all these electronic things, they don't know what is the reading of the temperature. They just come in a signal form. Okay, at this temperature, the signal may be higher or lower. Okay, so to make everyone understand easier, I will just say temperature. Okay, even though they don't detect temperature, they only detect the signal, right? So here, when the heating occurs, okay, if the flow doesn't move, okay, then the heat will accumulate in this area, right? But when the flow is of the liquid is flowing, okay, then it will disperse the heat over the other area, and you will sense differently. Therefore, you will know that the flow is actually moving or not, or at which how fast it has moved, right? So that operations depends on the concept of heat transfer, okay, within the fluid environment, okay. There are also temperature switches, okay, such as bimetals temperature switch, okay, we call it as a thermostat, thermocouples, okay. This one can detect the so-called temperature signal, okay, by using two different materials, right? And also the RTD, okay, resistance type of detector, okay, where when the temperature change, the resistance of the circuit or the wire now change, right? So that is the thermistor type of temperature. For others, you are now very familiar with this infrared temperature sensor. Whenever you go out, you will use this, okay, to detect your temperature, okay, whether it's true or not. The temperature, I'm not sure, but this is how it operates, right? If without calibrations, it may not true, okay? That's why again, in the later stage, you will understand that calibration is very important in these automations, okay. Then the last one is the semiconductors sensors, right? Now come to the last part where you deal with the handling of your operations, okay. You may need sometimes a timer, meter to count, or encoder to record the maybe the speed or the directions of your rotations, alright. So they are electronics or electromechanical switch, okay. That may, for a timer, it may it may activate in the sense of you want to delay the on or to delay the off, okay. So you may have on delay or off delay, okay, and it may operate using different mode or principles, okay, electronic, motorized, and pneumatic, right? So this is the pneumatic one, right? And in the pneumatic, you can adjust how the air can being exhaust, okay, throughout your operations, okay. And then for the electronics, you may see this kind of preset board itself, okay. But in the board itself, the main brain is this common chip that you have learned, I think, in your secondary school, a very basic 555 timer IC chip, okay. So that is how it is operate, okay. The main idea is still there, right? And also the motorized part, okay, you can control how long and so on, okay. The motorized type of timer, okay. So when you set it on, okay, so either is on delay or off delay. So when you power it on, right, what happens is that they will delay a number of time, a t time, okay, before it will switch, okay, or close the circuit, right? So this is how it operates, okay? On the off delay type, okay, so the relay power will how to say you will send the signal, but then after this period of off time, okay, then you will start to calculate how long it should delay before it actually cut off, right? So there is the on and off, okay. Depends on the on start of the power on part, okay, and the off depends on the off signal part, okay, of your relay. There are also cam timer, okay, depend on the cam profile of your timer itself, okay. This one you can adjust, okay, adjustable, programmable, so called, okay. And this is a example of 5 cam, okay. Inside they have multiple cam inside, you can detect change, and each of these will represent one throw maybe, okay, to control different circuits, okay. So, and you can program it according to your time chart, right? Yeah, okay. So this kind of cam timer may be available in your car as well, okay, to control the operations of your firing, okay, the firing of your engine, alright. Then also the counters, okay, to count how many rotations, or maybe hour meter, how many hours the power have been turned on, and so on, right? And the last one will be the encoder to generate a signal, okay, to represent a certain motions. That motions can be, if you want to interpret it, it can be in the form of the speed, okay, how fast it has rotated, or the directions of the rotations, and so on, okay. So these are the encoders, right? And this part will be the logic part that I believe you may have learned this in the microprocessors course, right? So that's concludes the end of this hardware part of the industrial automations and process, right?